Assalamualaikum warahmatullahi wabarakatuh. Hello guys, welcome back in my YouTube channel. Okay, I want to explain about deviation from perfect behavior, the compression factor, virial coefficient, and critical constant. I hope all of you enjoyed this video. Let's begin. Deviation from perfect behavior. The gas show deviation the perfect gas law because molecules interact with one another. A point to keep in mind is that repulsive force between axis expansion and attractive force axis compression. This figure. Figure 1c.1. The variation of the potential energy of two molecules on their separation. High positive potential energy at very small separation indicates repulsive at this distance. At intermediate separation where the potential energy is negative, the attractive interaction dominates. At large separation on the right, the potential energy is zero and there is no interaction between the molecules. Okay. Figure 1c.2. Experimental isotherm of carbon dioxide at several temperatures. The critical isotherm at the critical temperature is that 31.1 degrees Celsius. A. The compression factor. As a first step in making this observation quantitative, we introduce the compression factor Z, the ratio of the measured molar volume of a gas, Vm equal V per N, perfect gas. Vm decrease at the same pressure and temperature. Z equal Vm per Vm decrease because the molar volume of perfect gas is equal to RT per P, and equivalent expression is Z equal RT per PVM decrease, which we can write as PVM equal RTZ because for a perfect gas Z equal 1 under all conditions. Deviation of Z from 1 is a measure of departure from perfect behavior. Some experimental values of Z are plotted in figure 1c.3. At very low pressure, all the gas shown have Z equal 1 and behave nearly perfectly. At high pressure, all the gas have Z greater than 1. Z greater than 1. Signifying that they have a large molar volume than a perfect gas. Repulsive forces are not dominant. At intermediate pressure, most gases have Z smaller than 1, indicating that the attractive forces are reducing the molar volume relative to that of a perfect gas. This is figure 1c.3. The variation of the compression factor Z with pressure for several gases at 0 degrees Celsius. A perfect gas has Z equal 1 at all pressure. Notice that although the curve approach 1 as PZ, they do so with different slopes. The compression factor. The molar volume of a perfect gas at 500 Kelvin and 100 bar is Vm degrees equal 0.416 gm rank 3 mol rank minus 1. The molar volume of carbon dioxide under the same condition is Vm equal 0.366 gm rank 3 mol rank minus 1. It follows that at 500 Kelvin, the formula is Z equal Vm per Vm degrees equal 0.366 Tm rank 3 m rank minus 1 per 0.416 gm rank 3 m rank minus 1 equal 0.880. The fact that Z smaller than 1 indicates force dominate repulsive force under this condition. B. Virial coefficient. Now we relate Z to the experimental isotherm in figure 1c.2. At large molar volume and high temperature, the real gas isotherm do not differ greatly from perfect gas isotherm. The small difference suggests that the perfect gas law, PVM equal RT, is in fact the first term in an expression of the form PVM equal RT times 1 plus B accent P plus C accent P rank 2 plus etc. This expression is an example of a common procedure in physical chemistry, in which a simple law that is known to be a good first approximation. In this case, PVM equal RT is treated as the first term in series in powers of a variable, in this case P. A more convenient expansion for many applications is PVM equal RT times 1 plus B per Vm plus C per Vm rank 2 plus etc. These two expressions are two versions of the virial equation of state. By comparing the expression with equation 1c.2, we see that the term in parentheses in equation 1c.3b is just the compression factor Z1. Okay, you can see. Example of virial coefficient. To use equation 1c.3b up to the B term to calculate the pressure exerted 100 Kelvin by 0.104 mole oxygen gas in a vessel of volume 0.225 Tm ring 3. We begin by calculating the molar volume. Vm equal V per mole oxygen equal 0.225 Tm ring 3 per 0.104 mole equal 2.16 Tm ring 3 mole rank minus 1 equal 2.16 times 10 rank minus 3 m rank 3 mole rank minus 1. Then by using the value of B found in table 1c.c of the research section, P equal RT per Vm times 1 plus B per Vm equal 8.3145 joule times mole rank minus 1 Kelvin minus 1 times 100 Kelvin per 2.16 times 10 rank minus 3 m rank 3 mole rank minus 1 times 1 minus 1 975 times 10 rank minus 4 m rank 3 mole rank minus 1 per 2.16 times 10 rank minus 3 m rank 3 mole minus 1 equal 2.50 times 10 5 pa or 340 350 kPa, where we have used 1 pa equal 1 joule m rank minus 3. The perfect gas equation of state would give the calculate pressure 385 kPa or 10% higher than the value calculated by using the Fourier equation of state. The deviation is significant because under this condition, P per Vm 0.1, which is not negligible relative to 1. C. Critical constant. The isotherm at the temperature Tc 304.19 Kelvin or 31.4 degrees Celsius for carbon dioxide plays a special role in the theory of the states of matter. Table 1c.2 critical constant of gas. You can see. An isotherm slightly below Tc, as we have already described, at a certain pressure, liquid condenses from the gas and is distinguishable from it by the presence of a visible surface. Example: the critical temperature of oxygen signifies that it is impossible to produce liquid oxygen by compression alone if its temperature is greater than 100 155 Kelvin to liquid oxygen. To obtain a fluid phase that does not occupy the entire volume, the temperature must first be lowered to below 155 Kelvin, and then the gas compressed isothermal.